Now that we have an estimate for the variance, let's go through the steps we used for the z-test, but this time plugging in that s squared when we get there. And let's see what the implications are. Our null hypothesis is still going to be that the population mean is equal to some particular value. Our test statistic is going to be parallel to the test statistic from the z-test. In particular, we're going to take our quantity y bar. We're going to subtract mu, our null hypothesized value, and we're going to divide by not sigma squared over n, but s squared over n, which in this case is 100. So instead of writing 4 here, which was just some number I claimed to know, now I'm putting in an s squared. And I'm using here a combination of values particular to this situation where I have 100 women and I'm interested in their heights, and the notation we typically use. And I'm doing that on purpose because I want you to see that I'm substituting in there an s squared for that number that previously I assumed was known. Okay, so, and if I write this in terms of only the standard notation, there's our null hypothesized value, and this is s squared divided by n. That's my test statistic. Now previously we said that the reference distribution, when we knew the population variance, was normal. We said that y bar minus 65 divided by the square root of s squared over 100 should follow a normal distribution. That is almost true here. And for all practical purposes, it's true. So it's almost OK to write this. And really, I did write that because it's true. When I do this kind of test, when I use s squared as my estimate for sigma squared, I do just compare it to a normal distribution. However, technically, we should compare this to what's called a t-distribution. In particular, a t-distribution with n-1 degrees of freedom, which in this case is equal to 99. What is a t-distribution? If the sample size is pretty big, in other words, if it's a t-distribution with a pretty big degrees of freedom, it is just a normal distribution. However, for smaller sample sizes, for smaller degrees of freedom, the t-distribution is just like a normal distribution centered at 0, but with wider tails, with fatter tails. There's a higher chance you'll get a value that's further from the expected mean. Why is that? Well, there's a higher chance we'd get a value that's more extreme because we don't even know what the variance should be. There's some extra uncertainty here. The way to think about this mathematically is that the central limit theorem doesn't say anything about estimating the variance. The central limit theorem assumed that we knew the population variance. So we actually don't get to rely completely on the central limit theorem anymore. In fact, it's not even true that s squared will have the same distribution regardless of the population distribution. So the central limit theorem says regardless of what the population distribution looks like, if I repeatedly sample from that distribution and record y bar will follow a normal distribution. But the same thing is not true of s squared. If I repeatedly sample from a population and record s squared, the shape that I get for those values of s squared depends on what that population distribution initially was. If that initial distribution was normal, then I know that s squared follows what's called a chi-square distribution. But if that initial distribution is not normal, I don't know. So what does that imply? There's two implications. One implication is that we have to assume normality for this test. We did not have to assume that the population was normal when we did the z-test because the central limit theorem was showing us that the y bar would follow a normal distribution. However, we don't even know what the distribution of s squared would look like if we don't assume the population is normal. So here, for a t-test, which is what this is called, we do have to assume the population distribution was normal. The other implication of the distribution of s squared is that this whole quantity no longer follows a normal distribution. Y bar is normal. Y bar minus 65 is normal. But y bar minus 65 over this s squared quantity, which is not just a number, it's an estimate, follows this distribution that we call t. But again, for all practical purposes, that t-distribution looks a lot like a normal distribution. And if we have something like t99, it's still going to be true that 95% of the time, the values will be between -2 and 2 standard deviations of that mean. And so we take this quantity that we calculate here, We compare it to those cutoffs. If your t statistic, this is the t statistic, is greater than 2 or less than -2, then we know that our p-value is going to be less than 0.05. If our t statistic is greater than -2 or less than 2, we know that our p-value, our two-sided p-value, is greater than 0.05. Again, unless our sample size is really small, in which case we probably shouldn't be doing a t-test anyway, we should use a non-parametric test. Unless our sample size is very small, the t-distribution looks like a normal distribution.